So we can understand a 1 minus alpha times 100% confidence interval here. 95% confidence interval for sample mean population mean means we have 100 confidence intervals, and from 100 confidence intervals, 95 of the intervals contain the unknown population parameter. Here, because we are talking using normal distribution, that means we are talking about population mean mu or population proportion p. This diagram is showing you 20 confidence intervals. Out of 20, only one confidence interval which is away from this line. So this line representing the unknown population parameter mean. You know that for normal distribution, the mean value lie in the center. So in the center, we have this vertical line, except one, all of the 20, all of the 19 are crossing this line. That means these confidence intervals contains the unknown population parameter mu. So if it is 1 in 20, that means 5 in 100. So that means out of 100, how we can have 100 confidence interval? It is simple. Suppose you have a population of 100,000 people, and then you can you can select sample of 100, 100, 100. You can have 100 samples, or maybe 1,000 different people. You can have 100 samples. And from those 100 samples, you can construct 100 different confidence intervals. Why they will be different? Because your average sample mean will be different from one sample to other sample. Why we do construct of some confidence interval? Because point estimation is not much accurate. It do not include the percentage of efficiency or confidence. Therefore, we try to find confidence interval. Just example, you know, the daily temperature is like 22 degree to 34, 28 degree. So this is very common practice in our daily life, that we talked about interval values, like price of some commodity. For example, price of a laptop, $700. You will not say the price of this laptop of a laptop of particular specification is 700. Rather, you will say that the price could vary from 650 to 750 or 600 to 800. So this is our common practice in real life, that we talked about confidence intervals. Uh, but usually we say we are very sure. We don't say that we are 90% or 95%. So we convert the numbers into linguistics. I am pretty sure, I am very sure, I am just sure, and I think so. So these words are verbal representation of 80%, 90%, 99% confidence intervals. So linguistics can be converted into numbers. And if we talk about linguistics and numbers, so we can understand these confidence intervals. But because the linguistics and computational linguistics and natural language processing, you will study them in your 4th year. They are advanced topics, so you will see similar things there. Now, formally, there are confidence intervals for single population mean. For example, um, daily income, for example, monthly income by a freelancer on freelancer.com, or daily expenditure, daily government expenditure per day by a provincial government or a federal government. So these are estimation for the whole year based on a sample of maybe few days expenditures or few days income of a person. Two populations. When we want to compare the mean values, population mean values using sample mean values, for example, do you think that the male freelancers earn more than the female freelancers? It can be true, it can be false. So we use confidence interval and see whether the difference between the income is significant or not significant. So when I use the word significant, not significant, that means I am indicating that I am checking my statement whether the income is same for male and female at freelancer.com, or their income are different from each other for the male and female. Similarly, we can work out confidence interval for single proportion and two proportions. We can do the confidence interval for single variance and two variances. But the quality is that why I am limiting for one and two populations. why I am not extending my concepts to more than two populations. This is there is subject which is extending this concept to more than two populations, and that subject is called multivariate analysis. In multivariate, you can study confidence interval for multiple means or multiple proportions or multiple variances. But this is out of scope of this module, so we are not going to discuss that. When we will be talking about confidence interval for mean, you see from central limit theorem that the confidence that the sampling distribution for sample mean is normal distribution. So when we need to work out confidence interval formula for mu, we have to use central limit theorem and a normal distribution. But when we talk about variance, single variance or multiple variances, then you know that variance cannot be negative. It can have value 0 to infinity. So we cannot use normal distribution when we want to make confidence interval about one or two variances. Yes, so when it is single variance, we use a distribution that is called chi-square distribution, CHI, chi, but we read it KI, chi. So chi-square distribution is similar to T distribution and Z distribution, but it is used for variance testing, single variance or single variance confidence interval. If we will have two variances, we will use another distribution that is called F distribution. I have not shown the picture for F distribution here, but F distribution is also a right skewed distribution because it is also about variances, and variance cannot be negative. This is pictorial or picture representation of how it will look like when we work out confidence interval for mean or proportion, and when we work out confidence interval for single and two variances. Now we formally start with confidence interval or 1 minus alpha times 100%, like 90% or 95% 99% confidence interval for one population mean. But there are three scenarios. One scenario is that you know that in previous class we saw that if sigma square, which is the population variance, is known, then we can use Z distribution. If sigma square, number two, if sigma square is unknown but your sample size is larger than 30 or 30, that means again you can use Z distribution. But if population variance is not known and the sample size is smaller than 30, like 10, 15, 20, then we use T distribution. So following this concept that we developed in last class, we have one proof for the first confidence interval that will show how to derive the confidence interval. If you remember, in normal distribution, we saw that whenever we have to solve normal distribution questions, we first have to convert the data into from x to z. Here, x bar, it is not x bar to z. So from central limit theorem, we know that x bar, the sampling distribution for sample mean, follow normal distribution mean mu, variance sigma square over n. Here we have expectation of x bar is equal to mu, and if I take the square root of this term, sigma square over n, I get standard deviation of x bar is equal to sigma over under root n. Now, if I transform this into Z distribution, it is showing x bar minus mean of x bar divided by standard deviation of x bar. And if I say mean of x bar is mu and standard deviation of x bar is this. So here x bar minus mu divided by sigma over under root n. Now, because you remember when we transform, because it transform into Z distribution, then the mean of the Z distribution is 0. If you remember from normal distribution, mean of the Z distribution, which is standard normal distribution, is 0. Our confidence interval is 1 minus alpha. So this white region and this dark region separated by a point which is minus Z alpha by 2 value, critical value or point to a point, and on the right hand side this is Z alpha by 2. Whenever we talk about normal distribution, confidence interval using normal distribution, we will have same region on the left and the right. If it is 90%, we will have 5% here, 5% here. If it is 99%, 1% by 0.05% here, 0.05% on the right. How to find the Z value from this value? So we have a short way that we can find these table values directly. I am jumping to this table and it is showing if you are making 95% confidence interval, you will use 1.96. If you are making 90% confidence interval, you will use Z value 1.645, and for 99% 2.567. So you will just need these stable values for working with confidence interval for single mean or two means, or single proportion or two proportions. You see the probability that the unknown Z value, this Z contains the unknown mu, because it contains this mu which is unknown. Therefore, I am calling this Z as a random variable or unknown value. So this Z unknown value lie between minus Z alpha by 2, which is a cut point here, and on the right hand side Z alpha by 2, which is a cut point here, equals 1 minus alpha. So basically this dark region have two boundaries, minus Z alpha by 2 and plus Z alpha by 2. Then I put this Z value equals x bar minus mu divided by sigma over under root n. Now you have passed calculus and you know calculus. So if I want to solve this inequalities only for mu, I have to move this sigma over under root n on the left and right. I have to move this x bar on the left and right. And then I have to multiply by negative sign on the left and right. Finally, after solving, I will get a confidence interval for mu. Mu is in the middle. X bar minus some error, and Z alpha by 2, it's a table value, and sigma is 6, population standard deviation by under root n, less than unknown mu, less than x bar plus. So you see x bar minus some value, x bar plus some value. This is called the confidence interval for single population mean mu, provided that sigma is the population standard deviation, is given to you. So this is called case number 1, when sigma square is given. So when you know sigma square, you don't care about sample size. If we increase alpha, if you remember, I have shown you this. When we increase alpha, then we have this situation. Alpha means 1 minus alpha will be smaller. If I have alpha is equal to 0.01, so 1 minus 0.01 is 99%. If alpha is 5%, 1 minus alpha is 95%. If alpha is 10%, 1 minus alpha is 90%. So if we increase alpha, bottom to top, then the wideness or width of the confidence interval decrease. Alpha increases, width of the confidence interval decreases. Second thing, effect of the confidence interval based on sample size. Look at here. If I have a larger denominator, then this quantity will get smaller and smaller, like 50 minus 1 and 50 plus 1. But if I increase sample size, 50 minus 0.1 plus and 50 plus 0.1. So if I have a smaller second quantity, which is subtracted and added at x bar, then the confidence interval will decrease. Larger the sample size, narrower the confidence interval. So these are the effects you can verify by changing sample size in one question, by changing from 10, 20, 30, 50, 100 and 500. So this is one example. I randomly select 25 students for the math set scores and find sample mean is equal to 600. I know that population standard deviation from the population is 50. Population size is not given to us. See, we don't know how many students are there in the whole world or in the USA only. Find a 95% confidence interval. It is asking for 95% confidence. That means 5% is level of significance or lack of confidence. So alpha is equal to 0.05. Alpha by 2 is 0. Alpha divided by 2 is 0.025. And If I see what is the value for 95% confidence interval, it is showing I have to use 1.96. So I used here x bar, which is 600 minus 1.96. Sigma value is 50 divided by sample size, because we selected 46 students. Where is it? My fault. It is not 40 for 25. Suppose it is 46 students. And based on that value, mean minus this quantity and mean plus this quantity, it produced that for the sample of 46 students, we are 95% assured or confident that the population mean lie between 585.6 to 614.6. And we can represent this as a normal distribution with lower limit here 585.6 and upper limit here as 614.6. So this is case number 1. In case number 2, yeah, you can try these examples. In case number 2, we have everything same, and except that in place of sigma, we are using S. S stands for sample standard deviation. Look at this formula. Only the changes here, which is S. So because population standard deviation means the variance or standard deviation for the whole population, which is in practical life it is very difficult. So what we do, we replace the population standard deviation with the sample standard deviation and work out this formula. Everything is same except this thing. In case number 3, we saw that we have a smaller sample size. So when sample size is small and sigma square or sigma, which is population standard deviation, is unknown, then we have to use another distribution which is called T distribution. T distribution or T table have two things: n minus 1 degrees of freedom, and alpha by 2 is the confidence limit divided by 2, level of significance divided by 2. So we can use T table to work out. Everything is similar except that now in place of Z we are using T, in place of sigma we are using S. The derivation for this one and this one are same as the one we have seen in slide number 10. Same thing, just you have to replace T or replace Z in this formula. But we are not concerned much about the derivations. We will solve the numericals. So I will continue with the third video